you. Just while I set up and hopefully get it all running and share. I should hopefully. What can you see on your screen there, James?
Just see you.
Okay, that's good, but not what we want. So we had this running a second ago, and now it's not for some reason. We'll get there in a second. It's always the same, isn't it? No, it doesn't seem to be sharing or wanting to share. Can you see that now?
Yep, we see that.
Okay. Took a bit of time, but we got there. So is that the PowerPoint or the actual slides?
That's the slides.
Okay. So okay, is that still the slides?
Yep, it's gone down to number 23.
Okay. Okay, hopefully that should have all worked.
See your note presenter view, so see the notes and things. But...
Okay, right. I'll try stop share. Like I said, it was working like a second ago. We'll see if we can get ourselves back on slide. You would think after all these years of running this, it would all work. Is that okay? You got me now?
Yep, see the weird soils of witness.
Excellent. Okay.
Okay, cool.
Fantastic. We got there. So sorry about that, everybody. As you can see, I'm just manipulating my prop at the moment. So I'll put that one to one side. Hopefully you can see me. Welcome on to the talk. This is lessons for both me and for everybody else as well, I hope. But also a little bit, we were talking about this just before we started the talk, a little bit about how we need to maybe think about what we do about geotechnics, geophysics, geology, how we look forward about the information we've gathered over the past. So throughout the talk, I'm going to talk about some of the work I did 20 years ago, which is just as relevant today, if not more. Some of my experience of working with this weird material, and it is quite freaky in a good way, an interesting way. And also a little bit about what do we look for in the future and what can we do to help remediate some of these contaminated land legacies. And I think for me, probably most importantly, it's about what the Galligu is. Why is it a problem? And where is it? Because there's a significant amount of these contaminated land legacies. The interesting aspects, geotechnical aspects of the material itself, which is absolutely fascinating. And then how do we fix it? And how do we make sure, because this is a process that was around in the mid 18th century, how do we make sure that we're not creating another legacy for the future, 50, 100 years time? Because we're not understanding, monitoring, or most importantly, gathering the data and using it to make sure that when we do build on this stuff, as we are doing, that we're not going to create another problem further down the line. And there's a quote there on the slide, which always fascinates me. And this was the Royal Commission on Noxious Vapours that said, it's true that those coming to witness, and I'm not from the area, Cheshire area, you know, enter with a certain awe and horror and wonder if life can be sustained there. And that's very poignant from our geotechnical and sort of geological background, that actually those wastes are still there and we still have to make sure that we remediate and build in a way that gives a legacy for another 100 years or so. So for those of you who have heard of the Galligu, it's been around a long time, and it's basically a byproduct of the LeBlanc soap making process, soda ash process. And this was Nicholas LeBlanc, and there's a fantastic blog about his history. The poor guy killed himself in poverty as a consequence of the French Revolution, even though the industrial process he actually invented went around the world and made millions. So there's a very interesting historical lesson to us all. And it's a material that's gone through basically 3 different processes, 2 chemical process and extraction process, but its core inputs are all geologically related. It's one of those classical industrial processes from the Industrial Revolution here in Europe, which was designed in France and brought over to Britain, where we take brine, sodium chloride, and brine is the best form. So you can see why there was in Cheshire. Coal, and lots of it, so you can see the geographical elements coming through. Limestone, coke from the coal, and loads of coal to produce the heat in the furnaces. And essentially we take acid, brine, heat it up, and one of the byproducts was a hydrogen chloride vapor, which they just pumped out into the surrounding areas. We get salt cake, which is the common name for the output of that, into the second part of the process, where they add the limestone, the coke, and the coal, and we end up with this material called black ash. And black ash was the sort of black gold of its time. That was then used with water. You need plenty of water. You extracted the sodium carbonate as an aqueous solution, then dried it out to produce basically the dry soda ash, or the washing powder that was used in the detergent industry. But for every ton of soap or soda ash that was made, 2 tons of tank waste was produced, and this was just indiscriminately dumped everywhere, and that's what's produced the Galligu. So if you think of the sort of geographical connections around the UK, you need brine, limestone, plenty of coal, water, and also an environment to do this. And this is really one of the reasons why these industries built up in the areas we're familiar with. So the soda ash industry are predominantly around Runcorn and Widnes area because of the brines and obviously the Lancashire coalfields, but also the ports. But Glasgow, Manchester, particularly a place called Bolton, there's an interesting little case study about that. Gateshead up in the northeast, and also in the West Midlands. And I'm talking to West Midlands people here. I don't know where they are in the Black Country, but I believe there was a couple of smaller Galligu sites that are somewhere in the Midlands. And afterwards, when we have a chat about this, I would love to know where they are to add them to this lexicon of Galligu sites in the UK. And it's very interesting if you look at the history of part of that process is not only the geological and geographical, but also about basically the land and the people. We needed water for the processes, but we also needed the water to actually transport the materials to the ports. So you see the connection between the canals and the ports. We also needed the land and basically poor land to dump the wastes. And you need plenty of cheap and basically plentiful poor labor, people who needed the money, because some of the accounts you read about what they were doing, having to carry sort of hods of sulfuric acid around, and the environment they lived in really tells us a little bit about our industrial history and how, you know, we talk about countries in other places treating workers. We've done the same ourselves, and this is a legacy in our contaminated land of that. And there's a problem with the Galligu. I mean, I worked on this 20 odd years ago, and in the Runcorn Widnes area, there was a significant number of independent plants that used to take this Galligu tank waste and just dump it all over the landscape. And they actually used it as a infill for the salt marshes around the Mersey. So if you go over the Runcorn Widnes Bridge now, and you go from the Runcorn to the Widnes side, pretty much everything above sea level, particularly near the coastal marshes areas, is made of Galligu waste. And in some places, this is 10, 15 meters deep as a deposit. And it's sunk into the marshes and into the alluvial sediments of that area. And there's hectares of this. There's over 200 acres of known highly contaminated sites. But the whole area, the Runcorn Widnes Bridge is built on it, the railway line area, the landing areas of the bridge, the railway line, the expressway, freight terminals, shops, houses, commercial retail were all built on this waste. And the principle then was to cap it, seal it, and not worry about it. But one of the big problems is it gives off hydrogen sulfide. It stinks, basically. It really does. If you ever drive over to Speke Airport from the Cheshire side or the other way and come over and you get to Widnes and you go, what's that smell? So what's that? And you can smell the hydrogen sulfide in the air. And at the time, it was known, and even during, even the manufacturing people, the processors, the historical records show that this horrible smell of rotten eggs around these plants, it's not just Widnes Runcorn, basically blighted the whole areas. And we see that industrial legacy. It was known as the most contaminated site in the world in the 70s, this Runcorn area. Spike Island on the other side as well. It's a really important legacy for learning and understand how we deal with contaminated land. And there's nothing we can do about it. It's there. And what happens with the Galligu as a material is as rain, in particular recharge and acid, slightly acidic rain gets into it, it goes on to go as a chemical reaction, which basically takes hydrogen chloride from the atmosphere, particularly during the process of the plant itself. It reacts with the calcium sulfide and gives off hydrogen sulfide. But with that, because it was a landfill material, loads of other waste, particularly during the latter of the process and during the early part of the 1900s, was actually dumped with it because it was considered, oh, we'll just dump this stuff. And in the areas around Widnes in particular is known to be ordnance, asbestos, arsenic contamination. Anything that was not nice was dumped where these wastes were because it was considered as basically dead land, bad lands. And even though they initially wanted to try and remediate the sites, a lot of the problems we have now are more associated with what's in the Galligu rather than the Galligu itself. But I'll move on to that. So let me tell you a little bit of a classic legacy site, and there is a kind of geotechnical environmental end to this, but it's a fantastically named Nob End site in Lancashire, which is just south of Bolton. It's on the confluence of the River Irwell and the River Crowle. Now, this was a site that had a LeBlanc processing manufacturing centre from the mid-1800s, and was dumping this waste into this promontory. I hope my mouse is working. So the Nob promontory between the River Irwell and Crowle for best part of 100 years. In the middle of the 19th century, it was just demolished as a site and left in a relatively stable state for a long time. So I've taken this from Phil Sharple's historical blog and letter about this, and it's really interesting because he's followed this historically over pretty much 50, 60 years about how this site has developed and what's happening to it geochemically and environmentally. If you go back to 1961, the site's a barren wasteland. And yet, as it develops and sort of time moves on, in the 70s, it starts being left alone. It starts to develop its own ecostructure. So you start to see grasslands growing. And what you can see in the picture here, this sort of cliff wall on the sides of the River Irwell, this is all Galligu waste with some other waste in as well. And this whole area is just a mass of this waste, yet it's been left alone and left to basically sit there and start to self-remediate. And what I find very interesting about this is when we look at the sites that we're remediating now, which we'll get onto to a second, there is a natural process at the surface operating of the Galligu. It's calcium sulfate. And as it starts to be weathered down, it starts to turn back into calcium carbonates. So we're actually getting a geological change, a diagenetic, if you want to say, change at the surface as the stuff is being weathered. And as that's buried, we're actually creating a layered chemistry in the soil. And that becomes important when we think about the geomechanical properties a little bit later. If we look at this now, and this was taken, I took this from Google and from Dave Darlington's 360-degree image, just taken in the last year The whole site is a site of scientific special interest. It's actually a nature reserve. You can go take a walk around it. It's just off the other side of Little Lever near Manchester. And yet the site is one of the few places in the north where we get these calcareous grasslands. Some of the plants there are some of the rarest plants in this part of the world. And it's a haven for orchids. It's absolutely packed full of orchids. I think there's about 7 different species generally, but some very rare orchids as well. So leaving a site alone has caused this calcification of the top surface of the Galligu, which becomes important later geomechanically, and has provided a site that effectively, although very toxic, is not creating as much of an issue environmentally to the region around it, and it has recovered. To what extent it will remain recovered depends on what we do with it. And that's where I want to move a little bit on to probably the crux of the talk here, is what do we do with witness? What do we do with the areas that we're now developing? Now, it was a problem then, 100 years ago. It's a problem now. And you see the picture here, the New Mersey Gateway, which has been open to since 2017. This is a project that I was involved with on a peripheral side nearly 20 years ago. And the original planning of the Mersey Gateway was to have the bridge either upstream of the Widnes and Runcorn Bridge, which is there, across the sort of the western section of Runcorn and dipping into the Ditton Bank and the area of salt marshes round to the upstream side of Widnes. This is all made of Galligu waste in patches, with significant deposits of Galligu in this area. The alternatives were towards the upstream side of the Widnes Bridge, labelled 2 and 3 here, passing it over across the St. Helens Canal. And again, this area of marshland before the canal went in, also a major dumping area for Galligu waste. And even if you go further east and go out towards the upstream sections of the Mersey, there are areas of Galligu waste and further dumping grounds of other toxic wastes as you get out into the limits of the economic region of where the Mersey Gateway could go. Now, they chose this area roughly here, 3. And the important thing, and if you look on this picture here, all that area of the Widnes Runcorn, you've got the Manchester Ship Canal, all this area of the whole site here on the Widnes side is all Galligu with buildings on top of it. And this area is meant to be the regeneration focus of the whole of the Merseyside industrial area, this part of it, the Mersey Gateway. And we were involved originally on 2 small projects to look at using geophysics to actually understand some of these deposits and how we can guide Holton Borough Council at the time and their subcontractors and their consultants about methods for understanding and really monitoring and looking the depth of these deposits, because at the time they had no idea how deep they were, how extensive they were, and ultimately, what could happen as they change as we put greater degrees of load onto them. So I'm going to start with St. Michael's Golf Course, which is Widnes. So anybody who's been playing golf for 20, 30 years may have heard of this. This is a fantastic golf course. If you look at the top part of the picture, you can see myself and my colleagues there. We were doing radar surveys. This is on the very edge of the golf course, and this is Stewards Brook, I think it's called, Steward or Stewards Brook. And you can just see a sort of grey patch of stuff here. That's actually the leachate popping out a bit beneath the landfill cap of the golf course. And you go in here and it stinks. On a bad day, it reeks, and you can smell it for 20, 30, 40 meters away. And there's a housing estate just off picture here where the health problems associated with this leachate were well known for years. Now, it was built in the 1970s on top of up to 30 meters of Galligu waste. Now, I'm not a golfer, but I talked to some of the golfers here, and they said it's quite an unusual golf ball club because the Galligu waste has these unusual properties where, like a sloppy clay, it's not stiff. So the rub of the golf courses, of the greens, changes on the golf course over time due to the passages of buggy and people. And they say where people play, and if they use a particular route, it changes. And what we were particularly interested in is, can you map where the cap, because this is what they did, they just capped the materials because it was a sandy cap with topsoil. Can you map where the leachate is running and breaking out into the brook below, which we could do because the Galligu is quite an impermeable material. So a lot of the remediation during the 40s, 50s and 60s to try and reutilize these areas was basically put a load of soil on the top of it, cap it and see what happens. And this has become a legacy of the last 20, 30 years, certainly, as we now need to reuse these sites. And it's very interesting for this site that it's about 2000 we did the work on it. In 2004, it was closed because they found significant arsenic contamination. I don't know if it was in patches or distributed across the site, but it was told to close because of the environmental and health concerns. Yet later on in 2020, they've now remediated it completely, well, or operationally, and it's now actually a solar power farm generating 1 megawatt. And I looked online today, and there's actually plans to convert that and could create 3 times that energy for the local area. So how we use and what we do with sites is really quite important for our legacy thinking and what we do over the next 20 to 50 years to make sure these sites then don't become a problem again. Moving on, I like this material. So we're going to get into some geotechnics, and hopefully you can see me. I've rolled up my prop for today. So this is silly putty, and silly putty is a bit like the Galligu. So I'm going to go backwards on describing this. When we were doing some work, we were talking to people who worked on the site who work, I'll come to it, and they said, if they walk on it or drive over it quickly, nothing seems to happen. It's fairly stiff. It's like driving on stiff clay. But if they drive over it slowly, it starts to sink and move. Not the surface, but kind of feels underneath. And they used to say, if you manage to break it by, you've got a digger or something like this, or a big piece of heavy plant, you'll see in a freight terminal, and you break through the surface and you get underneath, it turns into toothpaste consistency very quickly. You can see that from here, from the plant. It's been basically starting to churn the ground up. It's broken the surface and gone straight down into the material. And that's because it's got 2 different geomechanical states or rheological states in reality. When it's oxidized, and it goes back to Nob End example, when it's been there and at the surface, and we get this granulated sort of calcium carbonate, mixed up, stiff, oxidized layer at the surface, it's got certainly pseudo-elastic, pseudo-plastic, but quite elastic properties. It's actually quite hard as a material, like a stiff clay. And it acts like what they call an anti-thixotropic or rheopetic, I think that's the right description, or negative thixotropic material, where when you put stress or shear stress rate onto it, it does strain, but it's effectively elastic. It's like a bouncy elastic material. And that means that the rate of strain that you apply, if you increase the rate of strain, it effectively becomes more viscous. Like silly putty, it snaps, becomes stiff. And that's a weird property. So as you're basically bashing this or agitating it quickly, in its oxidized state, it's stiff. So you can see where this is coming from, where people have driven over this fast with a big truck. It's stayed fairly rigid. But as it becomes wetter and more anaerobic, less oxidized, it starts to change its chemical properties. Now, I'm no chemist, but this is what I've read and what I've talked to chemist people about, and this is known. And it goes into a material state which is more positively thixotropic, where If you start to put shear stress on and it strains, and you keep the stress is the same, the strain, let's say, it basically starts to flow. It yields, but it yields and then flows. A bit like you see with some clays. And that means then that rheology-wise, if viscosity reduces with increasing stress, shear stress. Now, there's two analogies for this. There's two examples. The first one is custard. So I was just talking to Sebastian. If you feel like spending a good 15 minutes of wasted time, just look at running over a swimming pool of custard. And you'll find there's lots of videos of people literally doing that. If you put custard in and you run across the top of it on a swimming pool, you'll get to the other side. But if you stand on it, you'll sink. And that is a property which is like the anti-thixotropic properties of the Galligu in its stiff state, oxidized. The other state is the tomato ketchup state, which we're familiar with. Tomato ketchup, just out of a bottle, doesn't move. We have to agitate it to get it to reduce its viscosity and for it to flow. And this is exactly the same as the silly putty example. So the Galligu, when in a wet, less oxidized state, is a bit like the tomato ketchup. And when in a stiff oxidized state is a bit like the custard. So it's like the worst student dinner ever. It's a layer of custard on top of a layer of tomato ketchup. And we, as geotechnical engineers and our community, have to build, understand, and put for a long time legacy those geomechanical properties into our engineering designs. And the thing that's really important with this, and the thing that I found fascinating, is I got a chance to dig this out a little bit, and those properties were obvious. You could just start to squidge it, and it will just run through your hands into the pictures. And the important aspect of this is that when we're looking at traditional geotechnical work, we're very used to getting static figures. You can see there the chemical waste itself has been measured. It's like a stiff clay or sandy clay, which is slightly lower. But the moisture content, depending on the moisture content, and it's the strain stroke stress rates, depending on how you look at it, it doesn't matter. It's the time-dependent response. We're looking at very small strains for most loading applications. Yet as geotechnical people, we tend to test at high strains, deformation loading, triaxial, at strains which, if you look at which are beyond the natural conditions. But we also don't test at the variable strain rates well. So if we load, I'll take my silly putty that I've been remanipulating. We load our silly putty with a heavy load, and that's a constant strain rate. It will perform differently to if we have a light load and we push it up and down. We vary the strain and the stress rates on the material over time. If we vibrate this, and we vibrate this through traffic, through rail, through any relatively moderate load, and I'm talking moderate and spatially, we could end up with a different rheological and geotechnical property to what we would if we just put a low permanent load on, but take it off and on a periodic basis. So these are material properties that we have to understand if we're truly going to remediate this material. And it's very difficult to measure. It's very difficult to measure those low strain rates, and low shear stress rates in situ. Because obviously you take it out of the ground, you're changing it, you've altered its properties. And from a geophysical perspective, what we were asked to do is look at this to see, can we find the thickness of this? Can we find the extent? It has very high conductivity, so your electrical methods are pretty much out. It has almost the same density as the alluvial silts and clays that's sitting in. So density is an issue. And all the other techniques, radar, seismics, they're all very limited because it's too much like the ground it's in. So we had to find a different way to look at this, and a way that might give us information that supports the engineering and soil engineering design geotechnically. So going back 20 years now, so we looked at this problem and thought, well, what is it we're trying to get out of the data that we could collect? So we went through various, went through all the geophysical methods, and so basically hit on the fact the only way we can get some information out is going down to the core property that we're interested in. It changes its stiffness, its resistance to shear, depending on its state. So the only one that we could do that had the right resolution at the time was continuous surface wave seismics. Now, there have been other methods developed, some ASAW methods, they have developed over time. And I'll move a little bit later on in the talk about how we can take the lessons here and improve these for modern monitoring and evaluation. But we tried this on the site. So this is O'Connor's freight terminal. It was part of the development, and it was interesting just anecdotally that you can see in the picture there at the front of the site. This is clear, but it's still quite oxidized material. This has effectively been lying on the ground for 100 years and hasn't really been moved much. They built the freight terminal around it. And they were telling me that as they load the containers, you see different deformation patterns of the tarmac that's on there and the pavements due to the speed and nature of the loads, which fits with what we think of the geomechanical properties. So we did this trial, and we brought some team in to actually do a relatively basic survey that involves putting a sweep of frequencies into the ground and measuring the seismic response, and then determining the shear wave velocity through the Rayleigh wave velocity, and that moves us on to the stiffness. So going in a little bit more detail. So, and this is at the time, this was cutting edge technology at the time. We have a vibrating seismic source, which relatively commonplace now, and a geophone array, basic survey stuff. But what we're able to do is understand what, if we collect properly, the phase difference between the geophone's positions, knowing their exact location, and the fact that we are propagating in a known direction. And we sweep the frequencies roughly from 5 to 700 hertz in this instance, but now we can go higher and pick up what is the surface wave, the Rayleigh wave velocity, which we then convert to a surface shear wave velocity, with depth. And all we have to do is know the density of the materials. Don't have to know it highly accurately, but we have to know it with enough consistency to be able to do that conversion. And the theories here, but the important thing is the result is a stiffness profile with depth. And because the Rayleigh waves they develop and they sample a deeper section of the Earth with lowering frequency, we end up, once we invert, and we have to do an inversion process through that. So the mathematics has improved over last 20 years dramatically. We get very accurate results, but how representative? What is really important, and it's important for me, is the materials don't change over small periods of time. So even though we might not be fantastically accurate in an absolute way, the relative difference in S-wave velocities helps us understand the stiffness profiles relatively, and that allows us to have a before and after comparative monitoring process for any remediation we may want to do for any of the Galligu sites. So moving on, just some examples. Now, these are fascinating to me, and they were 20 years ago and still are now. If you look at the profiles, this is a typical profile from what was then a continuous surface wave seismic survey. If you look at all three profiles, you'll find that the top meter or so actually is performing like a clay soil would. It's getting stiffer, reduces a moderate level of stiffness. Shear modulus profile there, 50 megapascals, which is normal for clay to expect that. But interestingly, on all the profiles, we get this sudden drop at around about 2 meters. and the reduction, a significant reduction in the stiffness, or essentially its resistance to shear stresses. Then we start to get a relatively sort of gradual increase in the stiffness. And then on most of the profiles, and we collected a lot more than these, you start to see jumps. And you see interface effects, jumps as you get deeper. And I'm sure, you know, you're already one step ahead of me. We're starting to pick out interface changes in the stratigraphy of the land here. And if you look at the depths, and this is important, if you look at the depths that we're picking up just with this active method, we're getting down realistically to 12 meters, some cases 15, depending on how well the signals travel for the ground and how attenuated it is. But importantly, at the higher frequencies, and up to about 1 kilohertz is really where we go, you're getting that very near surface resolution. And that's important because as an active method, you're getting the depth and the accuracy and the shallow resolution and accuracy to give you a complete profile. It also means, because it's an active source, it's controllable, and you can repeat it on a regular basis. So obviously, this stuff was drilled, and it did quite a lot of work trying to understand it. And the closest survey we did, and this is the results from it, you can see that profile. The Galligu is stiff in the first meter-ish, as we'd expect. Oxidized, possibly churned over in the past, has converted itself into calcium carbonate, is stiff, is granular, is an oxidized state. It is acting like a clay would do, as clay soil in the natural environment. Semi-elastic, pseudoplastic, that sort of typical clay properties. But once we get into the water table roughly about 2 meters, it vary a bit, but not too much, roughly about 2 meters, it starts to lose its stiffness. And the chemical reactions that are happening in the ground, remember this is a marine, semi-marine estuarine environment. So there's chemical interactions and water interactions. This is close to the coast that have been happening over 100 years. This was a marsh, a salt marsh. So the chemistry is altering, the ground recharge. We're getting all sorts of sort of leaching and chemical reactions at the surface that are passing down a chemical leachate, essentially, into the lower part of it. The water table's reacting. It's in a sort of passing into an anaerobic environment. It's losing its oxidization state, and it's turning basically, for want of a better word, squidgy. And you see this in the stiffness profile as a sudden drop. You get some recovery, again, less to do with compaction, but more to do with, in my mind, chemical reaction. And then we start to see these jumps in the stiffness profile, which were very close to the known geology transitions into alluvial deposits, into fine sands, and into bedrock. And I didn't expect at the time that we would get this definition in stiffness or shear modulus with the natural materials to the Galligu, because the densities are almost identical. And even later on, as we did better density measurements, we did CPT related density, but we also did some gravity measurements here. We found that actually you don't need to have a very good handle on the density as absolute. As long as you have a good mass density, you bring out the relative changes in the stiffness profiles, because all the materials are very similar in density. So actually, any changes are related to the stiffness properties, the geomechanical, geotechnical properties. Not all sites will give you that, but it gives us a little bit of a hope for future monitoring. And so how do we fix this material? Well, predominantly, the current methods are we basically encapsulate it in concrete. We mix it with cementitious material. We create these little pellets, these hard pellets, and we put it back in the ground. And this was trialed on the site 20 years ago, and it's still the cement soil-based stabilization is still the preferred method. They either do it in soil, I'll give a little example in a minute, or they do it externally and put it back in. And this adds lots of problems into, say, about contaminated land sites, issues, materials in, materials out, etc. But the point is that this actually starts to remediate the geomechanical properties. It makes it stiffer. It's expensive. It takes time, but you can create areas, rafts or or blanket areas where you can remediate the materials. You're creating effectively a slab of more stiffer materials, but only at this time. So you're adding concrete, stabilizing. The Galligu material is still wrapped inside these balls. It's still there as part of the subsurface. And this is a sign. This is a really good case study. You can follow the link there. Regenesis has put this on, but this went into the 2018 Grand Awards. And this was the bus depot witness. And this was a Galligu site. And this is their conceptual model. I've taken this from the web. So, you know, all their information, not mine. And it's very much similar to the St. Michael's golf course and very much similar to the Common Freight Table and lots of these contaminated sites with effectively a topsoil mixed oxidized layer, Galligu leaching through the materials and some form of leakage pathway that's breaking out either at Springline, here at the Bridgewater Canal, down at Stewart's Brook, and also associated with other interventions, either waste, buried tanks, or utilities on the site. And they would have to remediate the site, and they looked at the soil cementation process. Yeah, this is for us, but they also wanted to do an activated carbon plume remediation program where they're stopping these leachates reaching the canal, which is absolutely great idea, fantastic case study, very much based in my mind towards the environmental aspects of this, with the geomechanical, geotechnical aspects. And their remediation strategy approach, which they applied, was to put an in-situ remediation, create the cement stabilization, mixing the soils. A company called Deep Soil Mixings were involved with this. I'm not familiar with them. And they created these these blankets, these patches of stiffened ground in situ that still contain the Galligu, but were a lot more stable. And they were small. They're in a grid of these small panels across the whole site, which is a fantastic idea. They put the plume stop barrier in to stop the leachate getting through, and they created what I think is an excellent remediated site to address the issues that we have now, and they're able to build on it. But, and this is my question, and this is why I want to open up to the future and the questions with you guys and as the geotechnical people of the future. Have we really, and I'm using the we here, not this company, but the we, have we really only considered what the long-term shear stress, loading and strain relationship is of this material, which is now flattened and moved, the Galligu, over time? Because these have now become relatively elastic panels with load acting on the soft material, which has spread the load and actually creates a relatively low strain percentage, but then puts a long-term loading stress onto this mass. Will we start to see differential movement of areas of the site, which was one of the problems they were trying to solve with this remediation technique? Once we load it with the building, what is going to be the long-term effect of that, given that these are in panels or they're distributed remediations and not a complete blanket? Will we then have to rethink the remediation strategy and have to remediate this in relatively short period of time? The expressway in Runcorn, which I drove along many times, moves yearly because of the Galligu underneath it. But they have to consider that, and they do. It's like any sort of sludgy site, for want of a better word. Is this really part of our process? Do we need to look longer term? And the stiff oxidized top layer has been removed. What is happening to that new surface layer? It hasn't had the opportunity to become oxidized and stiff and play a part of the process to help this remediation. Admittedly, they put new layers on top, but not in all places. So they strip some parts. So what we've done is we've exposed a site to a new chemical situation that may have been sitting there, like the Nob End site, for 100 years, actually creating its own self-remediation, supporting it. And the thing that particularly interests me as a geophysicist is, how are we monitoring this? How are we going to be able to evaluate this over time? We monitor sites that are at critical risk. With something like this site is not at critical risk, you could argue, so we don't monitor it. But it could be 20 years' time when these issues come again. And when you think that we're developing the Mersey Gateway and there's other sites in Glasgow are being redeveloped for commercial, retail, industrial use, we could have exactly that same legacy in the future. So just to finish off in the last couple of minutes, what can we do? Well, myself and my colleague Ian Jefferson at the University of Birmingham may even be on this call. Over the last sort of 10, 15 years, we've been looking at electrokinetic stabilization of London clays. And it's a similar situation. We get shrink swell, and without going into detail, we pump fluids into the ground, we charge the ground electrically, and the sort of anode-cathode relationship of it, the electrokinetics, moves the materials together and they cement the clay, making it more geotechnically stable in situ. It's been proven on the clays. We could apply those principles in the ground to the remediation, which means that we don't have the direct interference in the ground. We also need to look at how we monitor in a cheap way, in a consistent and long-term way. And this is where my research and the research we're doing at the university has really led me to thinking that our new world of data-driven science is perfect for this. We've got the baseline geodata. We can get the stiffness, and actually what we can use, we don't need to have active seismics, active high frequency, low frequency vibrating sizes. We can use the natural frequencies of the noise around us. It's moved on 20 years, the passive seismics, to give us stiffness profiles in the ground with relatively cheap instrumentation, basically geophones installed in the buildings and on the ground. And I do this, I've been doing it here regularly, and we can get the time-dependent change. It's a time-dependent change of the stiffness profiles that help us monitor it. And also bring in, and I use the words loosely here, societal data, bring in the data around the usages of buildings, the transport networks, to show us where the hotspots can be, the actual loads on there, the time dependence, to help us improve geomechanical and geotechnical models and models of the rheology of this material, so that they can put these into digital twins and we can learn through machine learning where the perturbations are going to result in something that's a problem, and where we have to basically do an intervention to solve that problem. So we're solving the future and making that data and understanding suitable for the future legacy issues, remediating the legacy rather than just remediating the issue. And I think that's important for us. And I think that's where the next generation of geotechnical science is going to lead to help us get these sites, which at the moment are left because they're problematic, to be remediated and then give us some benefit and value in their land. And it's about the understanding and the technology, and I'll sort of leave you a little bit of what we're doing at the National Buried Infrastructure Facility at the university. We're leading to this by providing that whole understanding geophysically, geotechnically, and with the physical scale models to be able to actually do this in a safe environment and apply it to site environments, so that when we go through trials and we get that data, the legacy of the future is about the legacy of our really high quality data and understanding, rather than a site that's just been left and we don't know what to do with it again, a bit like we did 100 years ago. So with that, I'll say thank you very much. I hope you've enjoyed it. I'm more than happy to have a good chat over this. Thank you very much.